Hi, folks. So this is just an unusual thing. I was at the first Russell Sage Summer Workshop in '94, and there are two other people here from that same workshop, and I've not been in a place where there have been three of us at the same time, I think since then, really. So it's David and it's Terry O'Dean. And as I was saying, I'm the least successful of the group. Well, if you think about it, though, the organizers, two of them won Nobel Prizes so far. So, anyways, a special group. The other thing is that all of us have papers in the Journal of Finance, although this has nothing to do with finance. I guess that's why they put me here. All right, this is a paper. It has to do with how people choose biased information sources and how they process the information. And the original idea, it's really Sevgi's idea. And the very cute design issue that she came up with is her design as well. But this is motivated by the idea that people are in different, they sort of have sorted themselves into information bubbles, and people aren't even talking to each other, and there's this bias. And we take the bias, but we strip it of all this other stuff that goes with it, like consumption utility from you want to believe a certain thing. We take these things away and we look at it in a really abstract environment and something that we used to do called lab experiments that I guess has kind of disappeared now, but not quite. All right, I like people to ask questions along the way. I know nobody does this here, but I like it, especially if you get confused by this part where I'm trying to explain something that's complicated, because it is complicated. So feel free to raise your hand, okay? So does this actually work? No. It does. No. Oh, look, it does. Okay, good. So I don't want to oversell this because you can say the experiment isn't really so close to the real world anyway, but news sources are often biased. You get a lot of these things that present facts differently, and it's done systematically. You can think Fox News on the one hand, you can think CNN perhaps on another hand, and people tend to watch the ones that agree with them. There's reasons for that. But there's concerns about the bias. As there are more news sources, it gets even more specialized, and people are self-selecting into these bubbles, okay? Maybe people internalize this basis, and most people think most news sources are politically biased, which seems like it's true, at least in the US. I can't speak for Europe, but it wouldn't surprise me. Confirmation-seeking behavior, that's really kind of what we're talking about. You get some utility out of getting confirmation. You could have non-instrumental value. It's not that you're getting information for its own sake, it's like you're hearing something that you want to believe. It makes you feel happy, okay? It could be that you trust news sources that align more with your prior, because you think they're more reliable, or maybe they're more informative. There's different ways that you get a confirmation-seeking behavior. There's papers on this. I think the first theory paper on this in economics was Rabin and Schrag and QJE, I think in 96 or 97. And they find that actually with the confirmation bias, even with an infinite amount of information, you could still hold to a false belief. So it could be persistent. Anyway, one way that you can have confirmation seeking is you have a selective search. You're only seeking information sources that are going to tell you what you want to hear, or there's selective interpretation. For example, you could think of two different fans of different football teams, and they're watching the same video footage of the football game. And there's a play, and one side's going to say, oh, that was a foul. He should have gotten a yellow card or maybe a red card. And the other side, no, it was perfectly fine. You tend to interpret things in ways that suit you. This is entirely human, okay? So this is some motivation. I'm not terribly interested that you buy the motivation, but that's where it came from. So we're going to have this experiment, and we're going to strip all this stuff away from it. We're going to look at how agents select among information sources. We're going to have two different possible advisors who are not real people, but they're computers that have been programmed in a certain way. So we don't look at strategic behavior by the advisors, which we could do, but that's down the road, okay? And we also look at how they interpret the biased information sources, how they process it. And this will become more clear as I get through the presentation. This is a bunch of sales stuff. I don't think it's terribly important, but there's some examples. So a consumer acquiring information about the quality of a product, okay? How do you get this information? A board member acquiring information about investment options, or one that I like because I'm so damn old, a patient acquiring information about different treatment options. So I tore all the tendons in my shoulder, and I got a little bump here now. And I went to a surgeon. Well, he says, yeah, surgery is a good idea, but I know he's a surgeon. So I get some advice from some other doctors, and you know what? Everybody else said, don't do it. I'm not doing it. But if you only go to some, if you want to have surgery, you go to a surgeon to tell you you need surgery, and then you have it. Anyway, I mean, that's a personal anecdote. Okay, so we strip all this stuff out. So it's an abstract setting. There's no attachment to a prior. I mean, there's no right, there's no left, there's no conservative, there's no anything at all. It's really abstract, okay? Which you can do in lab studies. It's one of the advantages of a lab study. The bias is transparent. You get exactly how the advisor is going to report given the true state of the world. You know the percentages, you know everything. So it's completely transparent, it's completely abstract, and we vary, well, this will become clearer, but we have two different situations. There's one that there's a distortion and one that's a filtering situation. In one case, if the advisor can either say this state or this state, and the advisor could be telling something that's not true. The other situation is a filtering situation where the advisor now can say it's this state or it's this state, or give a neutral signal which says nothing. But they have to tell the truth if they say it's this state or this state. And in one case, it's going to be the case that you want to go to the advisor that is, if you work out the numbers, that is biased. You want to go with the advisor that is biased more in the direction of your prior. That would be confirmation seeking. In the other case, in the filtering case, you actually want to do the opposite. So half the time you want the advisor that looks like confirmation seeking behavior, and half the time it looks like the opposite. And then the optimal type, there are some optimal types, will do the correct thing almost all the time. That's pretty vague. I'm going to get to something a little bit more concrete. But this is the idea. We took all this stuff away, and it's very neutral. And we're still going to find some results. Oh, there's a bunch of papers. Oh, some of the names might be here. I see Falk, I see Zimmerman. My name's up there too. I don't really go into literature reviews. Sorry. This is pretty simple. You have an unobserved state of the world. Think of it as left or right. There's a mapping from the state to signal. The signal, in principle could be left, neutral, or right. Okay? You have a prior that the state is right. P stands for the likelihood that the state is right, your prior. And you try to match the state. If you do match the state, you get money. If you don't match the state, you don't get money. Pretty simple setup. Okay? As I said, in distortion, you have bias through false reports. You don't have to tell the truth. Okay? It's non-verifiable. You could think of it as cheap talk. Okay? In filtering, you can't actually lie, but you can strategically omit information if you choose to do so, because it's verifiable information, like in a disclosure game. There's going to be two settings, and I'm going to show you the settings. So here's a definition. Sigma prime is biased to the right of sigma if, well, they cover the same space, and the distribution of posterior shifts to the right, first order stochastic dominance, when you replace sigma with sigma star, sigma prime. You guys are polite, you're not asking questions. Okay, finally we get to something. So here's two advisors. Actually, let me show you this. So here's an advisor. Let me tell you how to read this. So if the true state, for advisor A, if the true state is left, advisor A always reports left. never reports right. If the true state is right, the advisor reports left some of the time 1 minus lambda and reports right lambda. Is that more or less clear? Okay. Advisor B is a little bit different. Advisor B, if the state is right, always reports right. If the state is left, is going to report left delta lambda, and 1 minus lambda, going to report right. And here's a claim, which I can actually show fairly easily. This advisor, the B advisor, is biased to the right of A. And how can I show you that? I don't know if this actually works or not. It's so faint. Can you actually see that? All right. You're shifting weight. So look at the top row. Here it's 1 and 0. Here it's lambda and 1 minus lambda. So you've shifted 1 minus lambda from here to the right. And down here, you're shifting 1 minus lambda to the right, and you're getting 0 and 1. So this guy is biased to the, I don't like the word bias, but let's live with the word bias from now. This guy is biased to the right of this guy. Does everybody follow that? Okay. This is the easy slide. Okay. And now here's a claim that the optimal information structure, so the guy that you want to get the information from is the one that's biased in the same direction as your prior. Please. Yes, the prior is completely informative. So the way we implement it, you'll see it. You have, there'll be like 20 balls in a basket. And there's green balls and there's orange balls. And your prior is, this comes directly from, well, there's 6 orange balls and 14 green balls. So the likelihood that it's green is 0.7, right? That would be your prior. Yeah. And there's going to be a ball drawn out of there, and you're going to get some information about it, and you're going to try and guess the state. You're going to guess the color, basically. Does that help? Yeah. Good. Don't be shy about questions. So here's the argument. You want to avoid making mistakes. Where do you make mistakes? This is a mistake. This guy is reporting left when the true state is actually right. That's going to happen 1 minus lambda of the time. Here's one mistake. Here's the other mistake. When the true state is actually left, this guy's reporting right. Also 1 minus lambda. But if your prior is greater than 0.5, that means that you think that right is more likely than left. So that means that this error is going to happen more likely than this error, because the probability of left is less than 0.5. So you'd rather be here, you'd have a smaller likelihood of seeing an error than you do over here. David's following it. Anybody else? It's okay if you just accept it as being true. It is true. You don't actually have to do Bayesian updating or anything to see it. I mean, this is where it comes into play, is that you don't want to make mistakes, okay? And this mistake is going to happen less of the time than this mistake will. And it's the same cost, so. Terry's taking a picture. All right. This is the filtering case. This is much harder. So as you see here, this guy, if the true state is left, well, if he reports left, it's always left. If he reports right, it's always right. The interesting thing here is, what do you do with a neutral signal? So we've got lambda sub L and lambda sub H. Lambda sub H is bigger than lambda sub L, okay? And these are their reporting patterns. Now, there's a claim that that this guy here is biased to the right of A. And it's the same kind of argument. This is fairly easy to show. So if I could get this to work, all right. So if you look at the top row, what's happened? We've shifted some of this to here. So this was lambda, this is 1 minus lambda H, this is 1 minus lambda L, this is bigger than this. This is bigger than this. So we've shifted some weight from here to here, over there. so it's biased to the right. In the bottom row, you're shifting from here to here. So this is bigger than this, and this is smaller than that. And we've shifted whatever the numbers come out to, lambda h minus lambda L or something like that, from here to there. So both of these are moving to the right for the advisor B compared to advisor A. Thank you. And I'm not even going to go through this process given I have 10 minutes left. If you work this out, there are multiple cases. There are 2 cases. If you work it out, which I'm not going to do, you're going to find that now you should choose the other advisor optimally. And I actually could work it out, but it takes time, okay? So when the information structures are symmetrically biased and the bias is created via this distortion thing where you don't have to tell the truth, it's optimal to choose the information structure that's biased towards your prior. And in the other case, it's optimal to choose information structure that's biased against your prior. I don't know how in the world she came up with this. It's very cute. If you actually look at the derivation, it's very cute. So now we have a situation where people should do different things depending on the situation. And let's see what they do. There's an optimal type. We will look at types. There's an optimal type that chooses the optimal information structure. There's a confirmation-seeking one that always chooses the information structure that's biased towards the prior, which perhaps is what we see in the field, but what we see in the field, there's other reasons for it. It could be that you want to consume this information, it agrees with what you want to hear, and you've got a vested interest in hearing about it. We take that away. You could have the opposite type, it's always biased against the prior. We don't find that much of it. Curiously, we find people who have backgrounds in analytics are more prone towards this, which is funny. And then you have a certainty-seeking type, which is kind of rare. So they do they're opposite of optimal, actually. We're going to have 14 rounds we're going to have 6 different probabilities. Actually, no, it's not even up here. So I'll just tell you. We're going to have, there's probabilities 0.2, 0.25, 0.3, 0.7, 0.75, and 0.8. You're going to make a choice for each of these different probabilities. In one of the cases, it's going to be with distortion. In one of the cases, it's going to be with filtering. And then we're going to have 2 more periods that involve Blackwell ranking, where it's really pretty easy to figure out what you should do. And 90% actually get that right. Okay, so we're going to have these 14 periods. Then we're going to have a survey asking about different questions and try and see if we can match up the answers to behavior. Okay, so 2 computerized advisors providing information on the color. They choose which advisor. They've seen what the patterns of advice look like. And then we're going to elicit beliefs and guesses using the strategy method. We pay them. I told you this already. So this is how it looks in the chart. And this is how it looks in this chart. And this is the Blackwell ranked advisors, which I'll spend just a moment on. This is pretty easy. So here the bottom rows are the same. What's the difference in the top row? Here this guy reports left when the state is left 70% of the time. And here this guy reports left when it's really left 30% of the time. Which guy do you want to get advice from? This one. They get it right 90% of the time. They don't do so well with the other ones. This is what they actually see. Something looks like this. So this goes to your question. They see a bunch of balls. There's 14 orange, there's 6 green. This is the reporting patterns. So if the true state is actually orange, the guy reports orange 100% of the time. We didn't want to give them just probability numbers. The idea is that people don't know how to process. So we give them the visual with histograms. So which advisor do you prefer? And they answer the question. This is in the distortion. No, this is the filtering case. So now we have neutral, it's the gray one. So they get a chart that looks like this. And then you have questions. If the advisor said orange, what do you think the likelihood that the ball is orange, and so on and so forth. And the report, they answer these questions. We have data, a bunch of people. We present these things in blocks. Some of them observe distortion first, some it's the opposite. We give Blackwell questions at the end. The average pay is about $16 or $17 for about 80 minutes. Frequency of choosing the optimal advisor. This is our big success here, is the Blackwell case. It's about 90%. Okay? How do they do in the distortion case? Well, they're better than 50%, but they're not great. How do they do with the filtering case? Less well. I would say it's less than 50%, around 50%. And I have a personal theory about this. This is within subjects. And I think if you did this between subjects, it would even be lower in the filtering case. Why do I say that? If I'm a subject in an experiment and I say, okay, they're doing two different things, and I'm able to figure out that in this case I should choose this, I'm going to be very suspicious that in the other case I should do the opposite. I don't know how many people think like that, but it's an open issue for me. I could actually be looking like an optimal person when I only figured out half of it, but we don't know that. So they do better with distortion than filtering, though. Distortion is more towards the direction of confirmation bias. So result one, when they're not Blackwell ranked, they don't do that well with it, and they're more likely to pick information structures that are biased towards their prior, which is confirmation seeking. Guessing accuracy relative to the prior. So this is for people who choose the correct advisor. So this is how they do in the distortion case, and this is the upper thing here. Well, that's not what I wanted. I'm not too good with this. You see the white at the top. The top thing is how you should do the Bayesian benchmark. That's how well you should do with the information. They don't do quite that well, but they don't do that badly, especially in the filtering case. They do pretty well. This is for people who choose the optimal advisor. The people who don't choose the optimal advisor, they don't do very well. And there's not, this one case here, the optimal thing is actually 0, so there's nothing to compare it to. But it goes negative, so they do worse, okay? But we don't know for sure if it's because we're doing more sessions now to tweeze apart whether people don't do as well with the other advisor because they're not smart enough to have picked the right advisor, or because it's a harder problem per se. So we have to do something where they're assigned the advisor and how well they do. And that's, we're doing sessions. I think we did some on Friday. I think we're doing some today and tomorrow. My co-authors are doing it. So this is how some people did. They have patterns. We're going to classify people in different ways. You could have them with, if you're going to have a type, you could have it that in the 12 decisions, besides the Blackwell ranking ones, they made no mistake or make one mistake or two mistakes. This is the share of subjects who are classified depending on how loose your standards are. And there's going to be a mixture model, and I'm not going to talk about it. This, if you had a real random sample, this is how many people would be classified. Nobody over here, this tiny little bit over here, and not very much over here. So this is not random behavior. We're not observing random behavior. What do we get here? So if we do this type classification and we allow up to 2 errors, we get 37% are optimal, 35% are confirmation seeking, 9% are certainty, and 19% are contradiction. Contradiction is kind of in the opposite direction as confirmation. If you do the mixture model, it's pretty much the same thing. The random sample would be 25% in each case. That's what we actually get. If you look at it a little bit differently with perfect and less than 1 error and 2, it's a little bit different. In fact, this one with perfect, actually confirmation is by far the strongest. Okay, so there's a lot of confirmation seeking behavior here. Even though it's completely neutral, there's no real reason for it to be that way. Maybe you could argue that people are bringing that into the lab from their field environment, but we really did take things away, so it's not easy to say that. Less than half display optimal behavior. Actually, I'm surprised that so many did that well. Okay. Guessing accuracy relative to the prior. So the optimal type, almost by definition, does pretty well. So this is the lighter color is what the data we have in the data. So this is the improvement. This is how much it's improved. So let's say you had a prior of 0.7. This says that with the other information, you're actually able to get it right about 86% of the time. 0. Is that positive 0 or negative 0? Slightly positive. So you can see the optimal type does the best. These other types have some problems. I'm going to skip that. Everybody improves their accuracy relative to the prior, but the optimal types do the best. There's something with this is also shows the optimal type does the best, but I'm going to skip it. We're going to do some updating behavior, but I don't have the time, so I'm going to skip it as well. People displaying optimal behavior also state more accurate beliefs. Well, they tend to be smarter, actually. People don't do well with updating on the neutral signal. It's a tough task, okay? From the survey, we do have some stuff, and I'm almost done now. So these confirmation and contradiction-seeking types both report this to be their learning strategy in the experiments. I mostly considered whether there were more orange or green balls in the basket and chose the advisor that gave this color advice most often. That's confirmation. I mostly considered whether more orange and I chose the advisor that gave the opposite. That would be contradiction, okay? Neither is a good description of how I chose an advisor. Well, that's not so useful. And this matches pretty well with the typing in the experiment. So we have some evidence. We also find that cognitive ability, so we had CRT, a form of CRT. We had some Raven questions. We had some other questions. It's predictive of being an optimal type, so the Raven test, 2 stars, belief bias 2, and we did a Wason task 2, and it's not significant there. Confidence is also predictive of being an optimal type. That could have gone the wrong way, but that's what we got. Performance on these comprehension questions are also predictive of being an optimal type. Also confirmation seeking. And the analytical major is predictive of being contradiction seeking, which is kind of funny. The political attitudes and media habits are not very different across types, which is kind of a problem for us. And this is the summary slide. We have the strong evidence of confirmation and contradiction seeking, but much more for confirmation, even when we strip all this stuff out of it. That's it. Thank you very much.